see I'm already against some frustrating factors, and I know from using this laptop on certain projectors, it's obstinate. So it's only going to display either there or here, but not both. So I'm going to have to kind of turn to see what I'm actually showing you guys. But usually when this happens in the classroom, I turn myself around and sit with the students, and then I just pull a long cable out and I sort of teach that way. I don't have a choice, though, because this is the only laptop I brought. And I brought it for a reason. It's a Dell. If I switched to Linux, I suppose maybe it would work better. But hardware is the thing, and one of the things I'm going to show you, so I guess I should just forget about this, because this is not going to be an issue for me. So I'll just get started and then get into what I want to say. Well, actually, now it's showing up. Now I'm seeing the alternate screen, which is interesting if you're used to PowerPoint. So I've got a link to my website here, which I'll have another link later, but everything is on the website, all the software and packages of documents that go along with what's behind this project is all there. So it's a simulation framework. It's not a simulation framework that you would think of in production sense. It's a simulation framework in a purely educational sense because it was motivated by some needs. So in my overview here, I'm going to talk about the project learning experience and what was the motivation for me to create this. And then I'll get into some background on, I see I have a typo in it fixed there, GPS, not GSP. Some reason or another, my fingers don't always work good. And digital signal processing. Talk about the software, and I'm going to pass around, if people are interested, hardware. Hardware was not intimately involved in this first phase of the project, but it is on the back burner, and I do play a lot with hardware. I'm an engineer, and I'm a tinkering type engineer. If you've heard of the maker movement, how many of you have heard of the maker movement? So what do makers do? They make things. So making things in electrical engineering is electronics and development kits and software development tools. So that's factored in here. But then the Python framework, I'll show you some open and closed loop testing, conclusions, the future work, and if time permits, take you on a little tour of the code base and also show you some Jupyter notebooks that are running some simulations right now. So project learning experience, the link down below here is actually right into the website, and we'll maybe look at that if we have time at the end. And then you just look at the projects tab. This class is called Modern Digital Signal Processing, and it's taught once a year in the fall. And this last fall is when I developed this framework. You might say it was done on the fly. I had some students in the class, and since this is an engineering session, everybody that's an engineer knows of ABET. It's our accreditations board in engineering. I was just at ASEE 2 weeks ago, and we have to have a senior design capstone experience for students, and so I had a team that was partially in this class that said, we want you to be our mentor for our project sponsored by a local company. They were developing what they said was going to be a tightly coupled GPS INS tracking system. And I had not worked in a tightly coupled scenario before. I'd certainly worked on GPS before. So they said, oh, in a tightly coupled system, we have to demodulate and recover all these signals from GPS and then fuse them with the inertial navigation system and get this tightly coupled result. And they were pretty naive about the details of the GPS signals themselves. And as of most of you, unless you're in this area, probably are too. As a matter of fact, nowadays everybody walks around, and I do that too. What do you do when you walk around? You have your cell phone on and you're doing something with GPS, no doubt. You're using that all the time, right? Does anybody want to deny that they don't? It's de facto, but I think what was created in that system is something that, you know, a signal processing person deserves for their own knowledge. They should strive to want to understand some of the intricacies of that system because it is now legacy, but it's certainly a part of our lives, and a signal processing person should be interested in what makes it tick. So it's a hands-on project, and the idea was I wanted to implement a multi-channel code acquisition and tracking subsystem of a GPS receiver. That's always been a fascination of mine, and I've worked in this area in consulting before too, so I have a lot of pieces laying around of code. I was a MATLAB coder for a long time, switched to Python about 4 years ago, and so I've been rewriting a lot of my stuff and put this together into a package in a Jupyter notebook. So object-oriented programming factored into this, and I've been trying to get students in electrical engineering on board with Python, but also show them that they too can do object-oriented programming and take advantage of things that the computer engineers in our curriculum learn when they learn Java and C++. But I'm also a real-time DSP coder, so I know that plain old ANSI C works really fine for doing object-like programming too if you use data structures. Now, some of you are probably well familiar with that approach, and I do that in some other courses that I teach. So the hardware, though, well, first thing I want to pass around is why would I even want to try to create signal processing software for GPS when I can go to SparkFun Electronics, and I'll leave it, well, it's probably best in the bag, but I just want to hold something up, and buy for $15 this little GPS module as a maker, and it has 3 whole wires on it. It has a power supply, power lead, a ground lead, and then it has a serial terminal lead on it. So if you take this, plug it in, and I've got a USB serial port dongle on here. I can get all the data strings that come off the GPS, and you can parse them in Python, you can parse them in any language you want, and then you can figure out what satellites are up there, you can get all the navigation information, you could create something from that. These students ended up using that. The silvery top of that is the patch antenna, and you know, you still don't know what's going on inside, right? So if you have one of those, you're still a maker at a very high level playing with this. So the next step would be to go into a software-defined radio setup, and that's what I've got in this box, is a front end I can put on, and I can use in Python, I can use in other environments. It's the RTL-SDR. It's in the blue box in here. Then there's a GPS patch antenna in the black square, and then it's a preamp or amplified patch antenna, so then I had to make what's called a bias T to send a voltage up the transmission line to power the preamp and the patch antenna. And then there's a black battery case. So this particular RTL-SDR is a little bit more expensive, but the base unit is $20. So makers like playing with the RTL-SDR if they're in the software-defined radio. This one is more expensive because it has a higher precision oscillator, good for GPS, lower noise front end, also good for GPS. So what about GPS? Well, it started, actually I was working in industry back around 1979 when I first started for Motorola Government Electronics, and I didn't work on GPS, but the group I was in was doing stuff for the GPS satellites at that time. They were launched. The first batch was launched 78 to 85. It was called Navstar, and I've got that in, I can't, yeah. I've got that in smaller print here, but Navstar stands for Navigation System Using Timing and Ranging. Nobody talks about Navstar anymore, but when I worked back then, it was Navstar. But now it's just called GPS for Global Positioning System. There's 24 satellites nominally at minimum in 6 different planes that are inclined relative to one another, and they're in an orbit which is referred to as medium Earth orbit, or MEO. Some of you are probably familiar with those terms: LEO, low Earth orbit, MEO, medium. GEO is the one that's the most popular for most everything we deal with in comm systems, and in SATCOM, those are the ones that stand still. except small little perturbations that they do have. And then there's HEO, which is the high Earth orbit types. So MEO satellites propagate rather quickly around the Earth, and if you use a GPS and it hasn't been in a locale, you know that when you first turn it on, it takes a while to acquire and finally lock on to enough satellites to do navigation. This is a picture from a website. It's just showing you that, kind of motivating the need to have more than one satellite in order to geolocate. If you have a single sphere, you can think of a range measurement, and you cannot precisely put yourself on the surface of the Earth. If you have two satellites, you still have ambiguity. And if you have three satellites, you've eliminated essentially all of the ambiguity if you intersect the three spheres, but you still have an issue if you have time uncertainty in the clocks, and you do have some time correction that has to be made. But three satellites is the picture that most websites show you, that you get a valid solution, and then you have an invalid solution that you can throw away once you solve out the three equations and three unknowns. But if you have a timing inaccuracy, which you do have, then the fourth satellite is generally needed. And more satellites are better, because then you can get even improved accuracy. Another aspect of the MEO satellites, and in addition to that, there's another factor I'll mention in a second, is that satellites are in motion, so that produces Doppler. Doppler is something that has to be compensated for, just like mobile radio. A phenomena that most of us take for granted, again, is when we're rolling fast in a car and you're talking to a cell tower, you don't think about the fact that the Doppler is there, and the Doppler is actually challenging the ability to communicate, because you've got to track signals. So tracking of Doppler is required in GPS for sure, and that's something that I don't have implemented in my system yet, because I started it at a simple level. But the peak Doppler is around 4.2 kilohertz, which is definitely an audible offset frequency if you were thinking of listening to that. But it's a factor. And then, of course, if you're in motion, you've got more Doppler to track. The codes that I was set on using were what are called the course acquisition codes. The military uses the P code and the Y code, and then there's advanced GPS. But what we use in our applications, commercial applications and cell phones, is the CA code. It's a 1023-bit period code, so that just means that this pattern repeats every 1023 bits. In GPS, they're called chips, and chips is a terminology that came out of spread spectrum, which is a type of modulation that spreads the energy over a wide band of frequencies. What does it mean to be spread over a wide band of frequencies if you're not a comms person? Listening to AM radio, which most of you probably don't do, is talk radio, right? That's a very narrow band modulation scheme. The bandwidth of the message that shows up on the radio frequency is about the bandwidth, twice the bandwidth of the information. FM radio is much wider in bandwidth and sounds better for that reason. It's more immune to noise and so on. So spread spectrum just purposefully spreads things out even further. That's what Wi-Fi uses, and so on. So these codes come in a family. There's 37 codes in the family, as I'm thinking back, and they transmit on a carrier frequency called the L1 frequency of 1.57542 gigahertz. So the radio that I'm passing around can tune to that frequency with software, and there's a Python module that somebody wrote that's available that allows you to do captures, so I can tune the RTL-SDR to that and do a capture. But then the fact that I have these CA codes from the family of gold codes, which is making them have an orthogonality property, and that's the next bullet here. How many of you remember CDMA? It came before what? What are you using right now? It starts with an L. LTE, right? Long-term evolution. But before LTE, we were in second generation cellular, so we have things like CDMA, code division multiple access. So how could everybody talk to the base station from their cell phone simultaneously? These signals overlaid on top of each other and were nominally uncorrelated with each other because the codes were orthogonal. GPS uses that property so that we can have a number of satellites impinging upon us at the same time, and the signals overlay because they're mutually orthogonal. And it's this waveform cross-correlation that tells us that. So when we're tracking GPS signals, we have to correlate with a signal of interest for that particular space vehicle, and then we can lock onto it and see what the time delay, which relates to the range out to the satellite, is. So this is a picture. This is probably the most important picture that I gave the students in the project, and the most important picture for you to understand how the system works and what the software I've written is all about, the framework. The upper chart there is the transmitted CA code. It's on a carrier frequency, the 1.57542 gigahertz, but the baseband signal, as we refer to it, or you could think of this as bits on a bit pipe inside your computer, looks like this. So it's a transmitted code, and it's got the period of each chip is 1 over 10.23 megachips per second. And when you divide that out and look at the period of 1023 chips, the code repeats every 1 millisecond. So there's a new period of the code every 1 millisecond. At the receiving end of the link from the satellite, there's a delay, delta t, that I've just shown here. That's just the propagation time. And then the job of the receiver is what's in this third trace. It has a copy or a replica of the CA code. It's got the whole family of codes that it can generate. So it's going to correlate locally against the received signal, and all of these signals are simultaneously present, but when it correlates with one particular code, it's trying to correlate just one code from one particular satellite or space vehicle, as they're referred to, and it gets the last thing down here. It will get a strong correlation peak when it finds a code alignment with that one particular satellite signal that it believes to be overhead at particular time. So that's the job of the acquisition and tracking receiver, and that's the stuff that I've implemented. So I have to slide a local code along in steps, and then when it gets to a correlation peak, then it starts tracking it. And it does that across as many channels as I want to instantiate as possible, and that's where I took advantage of the object-oriented nature of Python. This just gives a little bit more math behind what the ultimate goal is. It's not to get the intersection of the spheres immediately, but it's to get what's called the pseudo range, which is the coarse measurement that's made on each of the signals. So that's what my software tool gives you, is a pseudo range. And once you have pseudo range for 4 satellites, you can solve for the 3 unknowns of X, Y, and Z, and also the time uncertainty. There's another time uncertainty that's sent down in a 50 bits per second message that comes from each of the satellites. So this is a high-level model of the framework. The patch antenna, if I was to implement that, is what I'm passing around. The RTL-SDR is the green. But at this particular point in the block diagram, I can replace the hardware with a software interface and a simulator interface, and that's on the next page. But this is the instantiation of multiple channels from the class that I've written. So a one-channel receiver would just instantiate one object, and an N-channel would instantiate as many as you want. The little receiver that I passed around is a 12-channel GPS. So it has 12 receivers in it, or correlators. And then you process in the blue box to get the nav solution. I don't have that implemented because I was mostly focused on, as I say, the orange box there. If I don't have the real RTL-SDR captured data, then I have a simulation environment, and that's all provided in the module as well. So I generate CA codes at the proper sampling rate to correspond to the hardware capture. And these are functions that are in some of my other pieces. I keep wandering for my pointer because it only shows up here. It doesn't show up here. So I resample the data asynchronously. I apply a bunch of distortion attributes if I want to, the Doppler, random phase. Add noise in to represent the actual noise of the receiver front end. And then, of course, if I have additional channels implemented, they would be down below. And they're all summed together to look like the composite signal impinging upon the patch antenna. The class CA search track is the main class that does the acquisition and tracking. So this is fairly involved. There's also another class inside that does what's called a numerically controlled oscillator. So that's a class unto itself. I don't know, most of you probably haven't heard of phase lock loops, but that's part of this. So that's the tracking loop is a feedback control system. It gets early, prompt, and late correlator outputs. So if I do open loop testing in my code, I will set thresholds so that it will not acquire and then go into the tracking mode, but this would be the output of the three correlators, early, late, and prompt. And this is the actual sequence of how you would write the simulation, set a carrier to noise ratio in dB, create some signals, throw in some noise, and then this is the CA code tracking function itself, which is a high level, what I call a top level, and it calls the objects inside to run a simulation or on stored data, and then you get output. So those are the three correlator outputs. If I actually let the threshold that will detect when I've brought the two codes into alignment, I'm stepping the local code against the received signal when it gets close. It then commences to track, so it changes modes in that class and begins tracking. And the tracking operation is kind of explained down here. The three correlator outputs, I'm trying to set the prompt correlator output on a large correlation peak, and then the two early and late correlators are going to be off the side of the peak, but if you form the difference between these two signals, you get what's called a discriminator or S-curve. And then you can track on that. You can then get the pseudo range. So, summary. Do I have time for the summary? Okay. Developed an object-oriented Python framework to go through the intimate details of GPS. And remember, when I started with this, the idea was these students wanted to do this in their senior design project the next semester, and I said, whoa, you guys have got a lot to do. You need to understand some of these details. So I was being a really generous professor, creating a project just for them, and the rest of the class had to put up with this, which is maybe not the best thing for me to do, but I said, you know, it's fun, it's DSP, and so I just kind of whipped it together and tried to adhere to some good coding practices, make something object-oriented and reusable, and let them see some of the complexity. And the future plans I have are to do more with the waveform capture. I've played with that some. I haven't gotten all the bugs out. I have successfully captured GPS signals. I'll maybe just show that for a second before I go for questions. This is just a Jupyter notebook showing you how I can capture by setting a capture interval, carrier frequency, sampling rate, and receiver gain. I can then go on to a different tab here. Let's see. Probably move this. This is a live capture at 1.57542 gigahertz through that preamp. So this is a collection of GPS satellite signals. How many are in there? Can you tell? You can't tell. But they're in there, and I started sifting through to do some work with them. So I guess I need to take some questions. The website is over here, and if you go to the website, you'll find the project down in there. That was shown, if I can get my finger to work, it's right here. I've imported Lab 6, which was actually a proposal I had for something I would have done as a workshop here, but and it imports some of the other modules, and that's available on another one of my websites, but that brings all the framework in, so now I can just live capture signals. I'm not doing real time here. I would like to start figuring out how to stream, but streaming has been done off this RTL-SDR by some other developers. You have to be very careful. I'm sampling at 2.4 megasamples per second, and that's how fast the data is streaming into the Python environment. So you've got to buffer and downsample and get things managed effectively. Yes, I haven't done it, but there's some papers on it. It's probably, you have to use C coding. You can't just do it in pure Python. Think of GNU Radio, if you're familiar with that. It can do that. There's issues, though, and I'm not really as much interested in that as I am just doing static waveform manipulation. That's probably that's where I started. I'm not trying to build what's in that $15 radio, because that's, that's there. It's just learning about what makes it tick is probably the most important thing. Oh, the tightly coupled? The students did a loosely coupled, and they did use Python. They did use the threads module, and they got things to work with that. But they weren't handling things at 2.4 megasamples per second. It was a much slower update rate.